Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Welcome back. We are getting into something today that I genuinely think is going to change the way you look at the world. And I don't mean that in a spiritual journey kind of sense, though it does get pretty close.
It gets weirdly close, yeah.
I mean it in the literal physical sense of looking at a table or a wall or your own hand and just questioning what is. What is actually there.
It's a fundamental shift. I mean, usually when we talk about science news, it's a faster chip or a better battery or...
a new species of frog.
A new species of frog, exactly. We're adding to the library of things we know. But today, we're talking about rewriting the preface of the book.
The preface being, what is stuff?
Essentially, yes, at its very core.
Because we're taught a very specific story when we're kids, right? I remember sitting in, 5th grade science class, and the teacher draws a circle on the chalkboard.
Oh, yeah.
She puts a little dot in the middle, the nucleus, and then draws these little orbits around it with other dots, the electrons.
The Bohr model. It's iconic. It's on the side of every science museum.
It is. And it's comforting. It tells us that the universe is made of Legos.
Right.
Tiny, hard, distinct little billiard balls that bounce around and stick together to make us.
It's what we call the particle picture, and it has been the dominant way of thinking about reality for, over 100 years. It's practical, it's intuitive, and it works. For almost everything we do in engineering, it works perfectly.
But you are here today to tell me that a team of researchers in Vienna has basically taken a sledgehammer to that Lego set.
That's a pretty fair assessment. Yeah. We are looking at a paper that was just published in Nature Physics from TU Wien. That's the Vienna University of Technology.
Okay.
And they have discovered a state of matter that, according to that standard particle picture, should be, impossible?
Impossible is a big word.
In physics, impossible usually just means we haven't found the right math yet. But in this case, the contradiction is, it's stark. They found a material that follows very strict geometric rules, what we call topology, but it does so without having any defined particles to actually follow those rules.
Okay, hold on. That's the headline that melted my brain when I first read about this. Geometry without particles. It sounds like saying you have a traffic jam, but there are no cars.
Or a smile without the cat.
The Cheshire Cat, yes. We are definitely going to get to that analogy because it's absolutely perfect. But before we go down that rabbit hole, let's set the stakes here. This isn't just about, winning an argument in a faculty lounge. Why does this matter to the person listening right now?
Because this discovery, I think, is the key to the next generation of technology. We are hitting a wall with our current tech. You hear about Moore's law slowing down.
All the time.
Our sensors are reaching their fundamental limits. This discovery, this breakdown of the particle picture, it opens a door to sensors that are virtually immune to noise. It opens the path to quantum computers that don't crash when you look at them funny.
Which they tend to do.
Which they do. And maybe most impressively, it shows us how we could steer electricity without using magnetic fields.
Steering electricity without magnets. How is that even?
It sounds like magic, but it's just advanced geometry.
Okay, I'm hooked. I want to understand how the cars disappeared, but the traffic jam stayed. Let's unpack this.
Let's do it.
So to really understand why this is such a shock, we have to understand what we thought was true. We need to talk about this particle picture, or as you called it, the approximation.
Right, the useful fiction.
Yeah.
So let's take a simple copper wire, the cord that's charging your laptop right now. When you think about electricity flowing through that wire, what do you visualize?
I picture a tube, a highway, and inside that tube there are millions of little glowing balls, electrons, just racing from the wall socket to my computer.
Exactly. You picture them as distinct entities, little spheres. They have a position. It's here. They have velocity. It's moving that fast.
Right. And if the wire gets hot, it's because those little balls are, crashing into things, creating friction.
That is the Grood model from 1900. It treats electrons like pinballs. And for, I'd say, 99% of electrical engineering, that model is fantastic.
They work.
It helps us design circuits, fuse boxes, toasters. But here is the secret that physicists don't really tell you until you're in grad school. It's not really true.
I feel betrayed. My entire high school education is a lie.
Don't be. It's a very, very useful fiction. In reality, inside that wire, you have billions of electrons interacting with billions of atomic nuclei, and they are all pushing and pulling on each other simultaneously. It's a quantum mess. It's a soup.
So how do we do any math if it's just a soup?
Yeah.
You can't calculate the trajectory of a soup.
You can't. So we use a trick, a very, very clever mathematical trick called quasiparticles.
Quasiparticles, which implies fake particles.
Yeah. Almost particles, or as if particles. Think of it this way. Imagine you were at a really crowded concert.
Okay.
Packed shoulder to shoulder. If you try to track one specific person moving from the back of the room to the stage, it's really hard. They're getting shoved, turned around, stuck.
Impossible, yeah.
But now imagine a small circle of empty space opens up in the crowd, a gap, and that gap moves toward the bar.
Okay, I can track the gap easily. I can see it moving.
Exactly. But the gap isn't a person. It's the absence of people. But it moves like a person. It has a speed. It has a location. So in physics, we treat that collective behavior, that gap, as if it were a particle. We give it a mass, we give it a charge, and we do the math on the gap, not on the whole crowd.
That is genius. So we pretend the collective mess is actually just a bunch of simple, well-behaved objects, and the math works out.
Precisely. That is the entire foundation of modern solid-state physics. We turn these incredibly complex interactions into simple quasi-particles. And this has been the rule. I mean, even the most advanced Nobel Prize-winning theories of the last decade have relied on this fundamental assumption.
What's the assumption?
That if you look closely enough, you can find a quasi-particle to hang your hat on.
So the idea is,
Yeah.
it might be complicated, but eventually when you boil it down, it acts like a particle.
Yes, that was the bedrock until now.
Enter the disruptor. The Vienna team. They were looking at a specific material with a name that it sounds like a distinct lack of creativity.
It does.
VU4SN6.
Purely descriptive. Cerium, ruthenium, and tin. It tells you the ingredients.
I feel like they could have named it Viennite or something cooler. But okay, CR4SN6. What makes this alphabet soup so special?
So it's what's called a heavy fermion system, which is just physicists speak for the electrons here interact really, really strongly. But the key isn't just the material itself. It's what they did to it. They cooled it down to temperatures that are just... they're mind-boggling.
How cold are we talking?
We are talking millikelvins, a tiny, tiny fraction of a degree above absolute zero.
Okay, so that's colder than deep space. Colder than the dark side of the moon.
Oh, much, much colder. And at these temperatures, this material enters a state called quantum criticality.
That sounds like the alarm that goes off on a spaceship right before it explodes. Warning, quantum criticality reached.
It's not quite that dramatic, but it's more like a state of supreme indecision.
Indecision. How can a material be indecisive?
Okay, so imagine a coin spinning on a table. When it's spinning, is it heads or tails?
It's neither. It's both at the same time, kind of.
Right. Usually in nature, the coin eventually falls, water freezes into ice, steam condenses into water, a magnet aligns north or south. Nature likes to make a choice. We call that a phase transition.
But in this material, it doesn't choose.
In this quantum critical state, the material refuses to choose. It is poised on this razor's edge between two different possible states. Let's just say magnetic and non-magnetic for simplicity. And it fluctuates wildly between them.
So it's flickering.
It's flickering, exactly. Diana Kirschbaum, the lead author on the paper, she describes it as a state where the material cannot decide which one it wants to adopt. And because it's flickering so fast and so violently, the interactions between the electrons, they effectively become infinite.
Infinite interactions. That sounds bad.
It means they're so strong they dominate everything. And when those interactions become that strong, our trick, the quasi-particle, it breaks.
The gap in the crowd disappears.
The crowd becomes a mosh pit, a liquid, a blur. You can no longer identify a distinct thing moving through the system. You can't say, here is a particle with mass x and velocity y. The mass becomes undefined. The velocity becomes undefined. The particle picture dissolves completely into a quantum soup.
Okay, I'm with you. We have a soup. No billiard balls, no quasi-particles, just raw, throbbing quantum chaos.
And this is where the conflict arises, because logically, if you don't have particles,
you can't have structure.
You can't have geometry.
This brings us to the other big concept we need to tackle, topology.
The 2016 Nobel Prize, a huge deal in physics.
Right. This word gets thrown around a lot. Topological quantum matter. It sounds very, very fancy. But at its core, It's about shapes, right?
It's about a very specific kind of shape analysis. Topology is often called rubber sheet geometry. In normal Euclidean geometry, a square is different from a circle because a square has corners and straight edges.
Sure.
In topology, we don't care about corners or straightness. We only care about one thing: holes.
This is where the donuts come in.
It's always the donuts. So imagine you have a ball of plated. You can squash it, you can stretch it, you can twist it, you can flatten it into a pancake. Topologically, the ball and the pancake are exactly the same.
Because I didn't tear it or poke a new hole in it.
Exactly. But if I want to turn that ball into a donut,
You have to poke a hole through the middle.
you have to perform a violent act. You have to tear the material. That tearing is a change in topology. So we classify objects by their number of holes. A ball has 0 holes. A donut has 1 hole. A pretzel has 3 holes.
And what about a coffee mug? I've heard this one.
A coffee mug has 1 hole, the one in the handle. So topologically, a coffee mug is identical to a donut. You can imagine squishing the cup part of the mug into the ring of the handle without ever tearing it.
Okay. I love that mental image.
Okay.
But electrons aren't donuts. They don't have handles. How does this apply to the quantum soup?
It applies to the mathematics that describe the electrons, and we map out all their possible quantum states, their energy levels, their momentum, their spin. That map can have a shape, and sometimes that abstract mathematical map has a hole or a knot in it.
A mathematical donut?
A mathematical donut, exactly. And here's the crucial part. Just like a real donut keeps its hole even if you dent it or take a bite out of it.
It's still the donut.
It's still a donut. A topological material keeps its special electrical properties. Even if the wire is dirty or bent or has some impurities, it is incredibly robust.
And this is why everyone is so excited about it for technology. It's bulletproof physics.
It is. But here's the catch. The entire definition of topological matter, the definition that won that Nobel Prize, it relies on describing the shape of the particle.
The shape of the dancers, not the dance.
Yes. You analyze the wave function of the quasiparticles to see if their mathematical space has a hole in it.
Okay, so syllogism time. Let's see if I have this right. Premise 1, you need particles to define topology.
That was the assumption, yeah.
Premise 2, this 4-EKN6 stuff in its quantum critical state has no particles.
Correct. The picture dissolves.
Conclusion. Therefore, 4-SAN6 cannot have any topological properties.
That was the prevailing wisdom. That was the logic. It's perfectly sound. If the particle picture breaks down, the topological classification should break down with it.
And this wasn't just some abstract theoretical annoyance. This actually affected the scientists in the lab, right? They hesitated.
It did. Science is done by humans, and humans have doubts and biases. There were some theoretical models, just math done on paper, hinting that maybe, just maybe, this material could host topological states. Yeah. But the experimental team at TU Wien, they were reluctant.
Why? Why not just look?
Because it felt like a complete wild goose chase. Professor Silke Buehler-Paschen, who led the team, she spoke about this. Why would you spend all this time and money and effort looking for a delicate, ordered geometric structure in a material that is essentially a chaotic, fluctuating blur?
It's like looking for a perfect snowflake in a blender.
That's a perfect analogy, it seemed.
Yeah.
Contradictory, illogical.
But they did it anyway.
Curiosity prevailed. Diana Kirschbaum, the PhD student and first author on the paper, she pushed to investigate it. And it's just that beautiful spark of science, right? The theory says X, my intuition says Y. Let's just ask the universe what it actually thinks.
So they fired up the world's coldest fridge. They cooled this stuff down to near absolute zero, and they went looking for the donut. How do you even look for a mathematical donut in a rock?
You look for something called the Hall effect.
Okay. We need to break this down. The Hall effect sounds familiar, like from college physics.
It's a classic. It was discovered way back in 1879. Here's the basic setup. You have a flat, thin strip of metal. You run a current through it, let's say from north to south.
Okay, so electrons are flowing down the highway.
Cruising along. Now, you bring a strong magnet close to the strip, with its field pointing, say, straight up. That magnetic field exerts a force, the Lorentz force, that pushes the moving electrons sideways.
Like a strong crosswind hitting the cars on the highway.
Exactly. So the electrons, instead of going straight, they start to curve and pile up on, let's say, the west side of the strip. That pileup of negative charge creates a voltage difference between the west side and the east side. We call that the Hall voltage.
Okay, so the simple rule is no magnet equals no sideways voltage. You apply a magnet, you get a sideways voltage.
Correct, that's the rule. But in topological materials, there's a twist. Literally. If the mathematical structure of the material has that donut shape, that topological twist, it acts like an internal magnetic field.
The material itself pushes the electrons to the side.
The geometry of the quantum states pushes the electrons. This is called the anomalous Hall effect. You see the electrons swerving to the side without applying any external magnet at all.
So it's like the banked turn on a racetrack. The cars turn, not because the driver is steering, but because the road itself is curved.
That is a perfect analogy. The Berry curvature of the quantum wave function acts precisely like a banked turn for electrons.
So the team in Vienna hooks up their electrodes to this particle-less soup, expecting to see what? Nothing.
If the logic held that no particles means no topology, they should have seen absolutely zero anomalous Hall effect. The cars shouldn't swerve because, well, there are no cars and there's no road.
And what did they see?
They saw a massive signal, a huge anomalous Hall effect. The electrons were swerving hard.
Without a magnet.
Without any external magnet. They found the signature of the donut.
But how?
You just told me the particles dissolved. The cars aren't there.
That's the breakthrough. That's the discovery. They found that the topology, the geometry, was surviving the death of the particles.
The smile of the Cheshire Cat, hanging in the air after the cat has faded away.
Precisely. And it gets even weirder, even more profound. They mapped out when this effect happened, and they found that this swerving, this topological signal, was at its strongest exactly when the quantum critical fluctuations were the most violent.
Wait a second. So the chaos wasn't destroying the geometry.
The chaos was creating the geometry.
That is completely counterintuitive.
It turns everything on its head. They did a control experiment. If they applied pressure or a strong magnetic field to force the material to choose a state, to stop fluctuating and become a normal, well-behaved material again, the topological effect vanished.
So if you fix the material's identity crisis, the magic goes away. Exactly. The donut shape, the topology, only exists because of the quantum criticality. The intense collective interactions between the electrons, that infinite mosh pit, are what actually generate the topological state.
So this is a fundamentally new thing. They had to coin a new term for it.
They did. They're calling it an emergent topological semimetal.
Emergent.
Yeah.
That's a heavy word in physics.
It is. It implies that the property arises from the collective behavior. It's not a property that's built into the individual pieces. It emerges from the complex way they dance together.
It's like consciousness, right? You can't find consciousness in a single neuron. It's not a property of the neuron.
Yeah.
But you put billions of them together and let them interact, and suddenly you have a mind.
That's a fantastic parallel. You can't find the topology in a single electron, but you put them in this critical fluctuating state, and this robust topological order emerges from the chaos.
They didn't just observe this, they explained it too. I read they brought in some heavy theoretical backup.
Yes, a team from Rice University in Texas, led by Professor Kim-Yao Si and Lei Chen. They did the heavy lifting on the mathematical modeling. They built a new theoretical framework that combines quantum criticality, the fluctuations, with the concepts of topology.
They wrote the peace treaty between chaos and order.
In a way, yes. And they proved mathematically that you don't need the particle for the geometry to exist. Professor Buehler-Paschen summed it up perfectly in their press release. She said, "A particle picture is not required."
That is such a dry, scientific way to say something that basically breaks reality. A particle picture is not required. It's like saying, oh, by the way, gravity is optional on Tuesdays.
It feels that big, because it generalizes the entire concept of topology. It moves it from being a property of matter, of particles, to being a property of fields or interactions themselves. The geometry is more fundamental than the stuff.
So we've established that the universe is fundamentally weirder than we thought. But let's bring this back to the why should I care factor, because you mentioned earlier this is a blueprint for new technology.
It is. A huge one. Now that we know the state of matter exists, we can go out and hunt for it.
Hunt for where? In other weird materials.
In a whole class of materials we were previously ignoring. See, before this, physicists who were looking for new topological materials, they generally avoided quantum critical systems. They thought, oh, that's too messy, the quasiparticles aren't well defined, the math won't work there.
They were looking for their keys under the streetlight because that's where the light was, not where they dropped them.
Exactly. Now we know the keys are actually in the dark, messy alleyway. And we have a map to find them. This opens up a huge class of materials, we call them strongly correlated electron systems, to be potential technological gold mines.
Okay, so what are we building with this gold?
Let's start with sensors. Remember the robustness?
The undentable donut.
Right. Because the electrical signal in these materials is protected by geometry, not by the purity of the material. It is incredibly resistant to noise. Temperature fluctuations, small impurities in the crystal, vibrations, they don't mess up the signal nearly as much.
So if I'm building an ultra-sensitive sensor for an MRI machine or a satellite telescope or a gravity wave detector,
you get a signal that is fundamentally cleaner and more stable. You get a level of sensitivity that we currently can't achieve with conventional electronics.
that's huge. Okay, what about energy?
That steering without magnets aspect, the anomalous Hall effect. Right now, to manage power flows or steer currents in computer chips, we use a lot of components that rely on resistance, which creates waste heat.
That's the heat that's killing my phone's battery life.
It is. Now imagine if the material steered the current for you, simply because of its intrinsic geometric shape. It's a frictionless process. It's what we call dissipationless.
Just flows like water down a perfectly shaped hill.
Exactly. It could lead to a new generation of electronics that are drastically more energy efficient.
And then there is the big one, the one everyone always talks about, quantum computing.
The holy grail.
We've been hearing about quantum computers for 20 years. It's always, they're coming next year. Why is it taking so long?
The short answer is because quantum states are incredibly fragile. A qubit, a quantum bit, is like a soap bubble. If a stray photon hits it, if it vibrates too much, if it gets just a little too warm, pop. The information is lost. This is a process called decoherence.
So we spend all our energy and resources trying to build these elaborate refrigerators to keep the bubble from popping.
Right. But there is a different approach, a theoretical one, called topological quantum computing.
Using the donut.
Using the donut. Instead of storing the information in the fragile state of a single particle, like the orientation of a soap bubble, you store it in the topology. You store it in the existence of the hole itself.
You can't pop a hole.
You can't pop a hole, exactly. You can shake the material, you could heat it up a little, you can have a defect, but the hole remains. The information is topologically protected.
So this discovery in Vienna, it's a huge step towards that.
It proves that these robust topological states can exist even in messy, fluctuating, hot quantum environments. It suggests that this emergent topology might be the best place to look to build a stable qubit that doesn't need to be perfectly isolated from the world.
It's like nature's own error correction is built right in.
That is a great way to put it. It's error correction by geometry.
I want to take a step back and just look at the philosophical side of this for a minute. Because we started this whole conversation with the simple idea that stuff is made of particles.
The Lego blocks.
The Lego blocks. And we have ended up with stuff is made of geometry that emerges from chaos. That's a big leap.
It's a transition from a material view of the universe to a structural or informational view.
It really feels like we are peeling back a layer of the onion and finding out there is no onion at the center. There's just the shape of where the onion used to be.
There is a theory in fundamental physics. It's speculative, but it's gaining traction, that perhaps everything is geometry. That particles like electrons and quarks aren't really fundamental things at all, but are just persistent knots in the fabric of space-time, or twists in an underlying quantum field.
So if you can somehow untie the knot, the electron would just vanish.
It would vanish, leaving behind flat space-time. And this discovery, the fact that you can have the topological property, the geometry, without the well-defined particle, is a strong piece of experimental evidence for that worldview. It suggests that the geometry is the more fundamental reality. The particle is just a temporary symptom of the geometry.
That is profound. It means that when I touch this table, I'm not actually touching matter. I'm touching a geometric rule that says your hand cannot pass through this region of space.
You are interacting with a topology that resists your hand.
Yes, I'm going to be thinking about that for a week.
Yeah, it's the kind of thought that keeps physicists up at night.
But in a good way. It means there is still so much to discover. We really thought we had the rulebook pretty much written.
And nature just handed us a new appendix.
Or maybe a whole new volume.
Probably a whole new volume, yeah.
Before we wrap up, I just want to give a shout out to the human element here again. Because it would have been so easy for that team at TU Wien to say, the logic says no, let's save the money, let's not run the experiment.
It would have been the completely rational choice, based on existing theory.
But they didn't.
Yeah.
They chose curiosity over convention. They chose to look in the blender for the snowflake.
And that is how all the best science happens. It happens when someone looks at a contradiction and says, that's funny, instead of that's impossible.
That's funny. Isaac Asimov said that was the most important phrase in science.
He was absolutely right.
So, for the listener who is currently feeling like their physical reality has been slightly dissolved around them,
Yeah.
what is the one big thing they should take away from all this?
I would say this. Don't get too attached to your models. The particle picture is a model. It's a tool. It's a great tool for fixing a toaster or building a bridge. But it's not the ultimate truth. The universe is more fluid, it's more emergent, and it's surprisingly more geometric than our simple pictures allow.
And sometimes you have to lose the cat to really find the smile.
I couldn't have said it better myself.
Thank you so much for guiding us through the quantum soup. My brain hurts, but in the best possible way.
It was a pleasure. Always fun to question reality.
And to everyone listening,
Wow.
keep asking the simple questions. Ask what stuff is made of. Ask why the light comes on. And when the answer doesn't quite make sense, dig deeper. We'll see you next time.